Walt Guy's biography is on the website. I hope you've had a chance to look at it. I'll just say briefly that I guess of all the lecturers coming, that Walt is the only one who is still actually working actively for NASA. He's head of Automation Robotics Division Chief at the Johnson Space Center. But that's not what he's talking about here. He's talking about the job that he used to do for about 20 years, which was head of Environmental Thermal Life Support and Crew Systems. And of course the Crew Systems includes all the space suits and the good stuff that I was fortunate enough to get to use. So I've got a personal debt of thanks to Walt. Aaron, I think you wanted to say a couple of things, so I'll pass the microphone to you.
Yes, I'd like to say a few words about Walt. We've worked together for many years, and Walt Guy has the very unique capability of being not only an outstanding engineer, technical person, but he also has a very unique capability of being a great or an outstanding project manager, program manager. No matter what task you gave Walt, he could deliver the product on performance, on schedule, and on time. He has that unique capability. He's done that from the Apollo program through the shuttle program. And I think you're really in for a treat to hear Walt talk about the environmental control system. He has a lot of information to offer you. So without further ado, let me turn it over to Walt.
Thank you, Aaron. As Aaron said, we worked together over several programs over a long period of time. I was noticing the picture. I'm sure that wasn't put there for me, but my current responsibilities are the robotic arm you see there. That's a shuttle arm. Of course, the station arms also. Grapple fixture over here on the left, and the little jet pack on the tumbling crewman there is part of my current responsibilities. The 20 years that Jeff mentioned, I was responsible for the development of the shuttle spacesuit. So it's like it was meant for me anyway. What I'd like to do is talk about the design. I know in the syllabus it said environmental control system, so where did all the rest of this stuff come from? If you go back in perspective, the Mercury, Gemini, Apollo program had the classical thing that aerospace calls environmental control system. It was basically a cabin system. It took care of the living quarters for the crew. But in the shuttle era, the responsibility of that system expanded to include more than just the cabin, and thus the very long, hard-to-say name. These are the subsystem elements of the environmental, thermal control, and life support system. The first area I'm going to, what happened here? There we go, sorry. These are the areas, the subsystems. The first area is the cabin atmospheric revitalization system. This is a long way of saying to take care of the atmosphere in the cabin. Humans are pollutants, and this is the system that takes care of that. The cabin atmospheric pressure and composition. This is obviously the maintaining the pressure and enough oxygen for breathing. The third is the cabin thermal control, and that is the classical environmental control system. But for shuttle, we've added some functions. One is the water and waste management subsystem. There's some hygiene functions required. There's some recharge of the spacesuit's backpack, management of the fuel cell water system, because the fuel cells are the electrical power supply and provide a lot of extra water. Also, the vehicle at this point has a dedicated active thermal control system that takes care of all of the systems in the vehicle, not just the cabin systems. And then last is the airlock support subsystem. This is the EVA crewman's portal to space, and so the environmental, thermal control, and life support system covers all these areas. What I'll do is go through each one of those. The first is the cabin atmospheric revitalization system. Its functions are CO2 and trace gas removal, humidity control, environmental cooling, and atmospheric circulation and ventilation. Again, I'll talk each about these, but I do want to mention that there is a uniqueness about space in that there's no convection, so circulation is important. Also, because of the fact that there is no convection, getting rid of the body heat, the latent heat, requires ventilation of the crew. So each of these areas ended up as part of the system design. This is an overview silhouette of the orbiter. I'll use this throughout the presentation. As you can see, the part of the system we're talking about now, the atmospheric revitalization system, is located up front where the crew is. It's beneath the floor. We'll be talking about the systems in the remainder of the orbiter as we go along. This is the simplified schematic. I'd like to start at the cabin fans. These are redundant. Each fan will do the job. The next in line is the CO2 scrubber, followed by the cooler, the cabin heat exchanger. There is a bypass around that for control of the amount of cooling that's needed. As you're aware, the shuttle can fly with few or many crewmen. It turns out as time has gone on, we fly pretty much a full complement, but the original design was to fly a small number of crewmen. Also, this does give you temperature control. The same heat exchanger provides the condensation of the water from the atmosphere, therefore you get humidity control, and then that's collected. The gas continues on. It's now chilled and is provided out to the flight deck and the mid deck to the crew. Then the gas from the cabin is then drawn back in through some flight deck avionics and back through the fan. So this is the basic system schematic. I might pause here a moment to sort of explain the role of the government in the development of the shuttle. As you know, the prime was Rockwell. It was their job to build the vehicle. But the government philosophy, management philosophy, was to have ownership of the technical aspects of the design. So we had basically no excuse. If it didn't work, it wasn't because the contractor did something wrong. We had to have ownership. In fact, Aaron, as the project manager, would probably look to us first as the reason for a problem as opposed to Rockwell, because we were the conscience of the program. So we should have made sure they didn't do it wrong and provided whatever technical insight to Aaron to make sure he made the programmatic decisions to make sure things weren't done wrong. So very early in the shuttle program, I was responsible for an engineering organization, and that engineering organization wanted to own the design of the environmental thermal control and life support system. So I don't have to get used to this, won't I? Okay. We acquired a chamber. This is a near atmospheric chamber. It's square, so it's obviously not shaped like the orbiter cabin, but the volume was appropriate, and it did allow a sealed environment for testing. It would take a couple of psi delta P is about all it would take. We developed a...
We did run it at 10P 10.2, right?
No.
That was a different one?
Different one.
Yeah, okay.
We developed an environmental control system, or an atmospheric revitalization control system, and placed it inside to do early testing. As you can see here, this is the fan package. The CO2 scrubbers are here, heat exchanger package over here, and you can tell we're not current in terms of calendar-wise. The CO2 and trace gas removal, the requirements were to maintain less than 7.6 millimeters of mercury. This is certainly to provide a habitable environment for the crew. This is higher than sea level, but the medics agreed that that was a completely adequate level for CO2. The CO2 absorption came from the humidified cabin gas, so the system had to accommodate that as a feed stream. The absorbent was selected was lithium hydroxide. The equation was the lithium hydroxide reacted with the CO2 to produce lithium carbonate, water, and heat. And this was a single-use system. It turns out that the lithium hydroxide was an old solution. The previous spacecraft had used the same solution. But pretty much their solution was unique purchased production of lithium hydroxide. When we entered the shuttle era, we were hoping for a long duration, and the idea was to use the commercial products to get away from special production. And so we looked around, and the Navy was producing a screened special production run for their submarines. So there was a lot of use there. So the production was reasonably up. So we decided to use the Navy grade, and so we brought it in and put it in the test bed that I just showed you and did some tests, and it didn't work worth a darn. You notice the loops here show that our canister use of the canister was much more rapid than we had hoped for. The nice, beautiful, deep loops here are a process that we developed to screen the Navy LIO so that we didn't have to create a new production capability, but were able to test the LIO that came off their production line and get a LIO that was much more humidity tolerant. The key here turned out to be not the chemical itself, but its ability to produce good performance over a wide humidity range. So we were able to screen that and make that a viable non-special production run LIO. The lithium hydroxide, I said, was an old solution. All previous spacecraft have been pretty short mission, and even the shuttle was a short mission. But the specification for shuttle said that it should have the capability of going 28 days. And 28 days is not a short mission, at least not in shuttle parlance. So the engineering part of the organization said, well, why don't we go with a regenerative system? Skylab had just been successfully flown with a regenerative system, something we didn't have all this expendables, because 28 days worth of lithium hydroxide for 7 crewmen fills everything up with lithium hydroxide. There's no room for anything else. So we began to look at a regenerative system that could be used. Actually, it was proposed as part of the original shuttle development, but at that point the 28-day mission was considered a special case, and the design case was the shorter missions. And in fact, there were even projected to be a lot of short missions. The idea that the shuttle was a space truck that would take stuff up, dump it out, and come home. And so the lithium hydroxide was a lighter system than a regenerative system. So the lithium hydroxide was placed into the vehicle as a basic design. But when Spacelab era came along, we needed longer missions. We flew about 4 or 5 times in this 13 to 16 day range. And those missions did require a lot of lithium hydroxide. And so it was proposed to use an absorbent that was regenerable, and the one that was selected was a solid amine. The absorbent is a polymerized ethylene amine. Its designation is RNH, and I don't really know why. The absorption actually comes in 2 steps. First is a reaction with water to create the Freon, and then that is then reacted with the CO2 to give you another free ion, but the CO2 is now captured. The desorption then with the heat and vacuum gives you back your original amine. So if you pack this in a bed, and what we used was an expanded metal foam heat exchanger that you could fill all the holes with the solid amine, and put the passages adjacent to each other, so that you could use the heat of absorption to do your desorption in your other side, and all you need to do is expose it to vacuum. So it was a very simple system. It worked fine for the 4 or 5 missions, 3 or 4 missions. I'm not sure how many missions it was used. But it was an adjunct. It was added in, put under the floor, then it was taken back out when it was no longer needed, because it was just wasted load. Yes?
the lithium hydroxide, the product, the LiCO3, is that a solid form, gas form?
No, it's a solid lithium carbonate.
Okay, and that goes in the canisters that you remove?
Right. When you remove the canister, it's a big lump. Yes. Okay. Finishing up the CO2 and trace removal, we go to the trace removal. We use the simple system of activated charcoal, and in fact it's packed into the same canister that the lithium hydroxide is packed into. It is a single use. There is a configuration, I believe now operationally, where the entire canister is lithium hydroxide, is activated charcoal, so it can be used for cabin gas cleanup. So if you had an issue that you needed to clean the cabin up, you could do that with a canister of just charcoal. The next area is the environmental cooling and humidity control. I mentioned on the schematic that we have a cabin heat exchanger. The front part of the heat exchanger basically is your reduce the cabin gas temperature. The back end of the heat exchanger is where the condensing occurs, because we get the gas below the dew point, and therefore the water drops out. The heat exchanger has the characteristic that as the water collects at the outlet of the heat exchanger, there were some holes drilled, actually, in the fin passages, so the water can be sucked out. And it has the nickname slurper, so it slurps the water out. It takes about 2% of the flow. So as the cabin fan produces the flow through the heat exchanger, about 2% is siphoned off in the slurper, and that carries the water to the gas. Water. Looks like I don't learn. The centrifugal water gas separator. This is a device that basically spins the airstream. It's an airstream with water entrained. It spins the airstream, the water goes to the outside, it's collected in a trough, and there's a pitot tube in the trough that the water impinges on, and we get about a 40 psi delta head with that. It's just a pump, basically a pitot pump. The atmospheric circulation and ventilation is the next part of the system. As you know, we're still in atmospheric revitalization. There are the redundant fans that I mentioned. Each fan will do the job. There are also flight deck and mid-deck duct system. This is a picture of the duct system. It looks very complicated, but only several points I want to make here. This is the atmospheric revitalization system I mentioned before. As you see, it's below the floor. This is the mid-deck here. This is the flight deck. So it's below the floor of the mid-deck. The gas is exits. The heat exchanger goes up. There's some mid-deck, aft mid-deck ventilation exhaust. It goes on up and to the flight deck, exhaust on the flight deck. Also, there is a section that goes on the forward side of the cabin through the forward control console and blows in the face of the crew. The return is back through some avionics areas, provide cooling, and then back down to the system. So this is a complicated picture, but really it's a very simple flow system. This becomes important later in our discussion because good mixing turned out to be a really important parameter, not just cooling. Okay, the second, remember we had 6, this is the second element. This is the atmospheric pressure and composition control. The first job is the 14.7. Shuttle selected sea level, the idea being we could not have a lot of special designed equipment. Shuttle was intended to be a less expensive spacecraft than the previous ones, and so a sea level atmosphere gave us no questions about human survival and gave us a lot of opportunity for using more standard equipment and not specially designed equipment. There was a requirement, though, for an 8 psi total control, but this was only for an emergency deorbit. The problem statement is that you've gotten a hole in your cabin. Don't know how you got it, but you have it. And the idea is the system has to be able to sustain the crew for a deorbit. And I don't know who made up the number, but 169 minutes is the number. So we have an emergency return, 169 minutes. The system has to be able to accommodate that, keeping the pressure, the total pressure at or above 8 psi. So there has to be enough flow capability, enough consumables to do that. The half-inch hole was a programmatic decision. I can't speak for that, where the number exactly came from. It probably had to do with meteoroid debris kind of analysis that said what type of hole you could expect. But anyway, that was the design for the system. The next aspect or element of the system is the O2 N2 partial pressure control. At the total pressure of 14.7, we wanted sea level, which is about 3.2 psi oxygen. At the 8 psi, we wanted it to be survivable, but the oxygen could be less. Obviously, people live in Denver, right? So it all works. There are also crew breathing masks, which can be used in conjunction with low oxygen partial pressure. The cabin had to have both positive and negative relief. It had to store the oxygen and nitrogen, and it had to provide pressurization for the water management system. Remember earlier I talked about the more pervasive requirements. The water and waste management system now is placing requirements on the atmospheric pressure and composition control. This is a silhouette again. We're basically, here you see the oxygen tank, which is 3,300 psi oxygen tank. There's nitrogen tanks on both sides. These are high pressure tanks, all 3,300 psi. The relief valves are shown here, and there's a O2 N2 supply panel which has all of the valves and regulators and everything on it. This system, however, though, gets most of its oxygen from the cryogenic tanks. So that is only just shown as an inlet. These tanks are basically part of the power control system. So electrical power is hydrogen and oxygen fuel cell. So we use a lot less oxygen than they do. So the storage was integrated, and then we use the oxygen for most of the uses comes from the main tanks. So this is a schematic. I'll start right there. This is the cryogenic system. This is the main cryogenic system. This is not part of the tankage of the pressure and composition control system. It goes through a restrictor. This is stored in a supercritical state, so the delivery is somewhat limited, and so this goes through a restrictor so that we don't decrease the pressure too fast in the cryogenic tank. It comes on down through a regulator that regulates down to 100 psi, and that comes on down to two regulators. One is the normal regulator, the 14.7, and the other is the 8 psi regulator, both of which are available for depending on which cabin mode you're in. If you go over this way, you see the nitrogen. The nitrogen goes through its own regulator, and it's regulated at 200 psi, and that's important because that's contrasted to the 100 here. Next, the nitrogen goes through an on-off valve, a solenoid that is connected to partial pressure sensors of oxygen, and then it goes to the same regulators. So if you're making up cabin gas, you have to make a choice as to whether you want nitrogen or oxygen, and that choice is made by this system and a simple on-off valve. So there's no sophisticated control system. This is a simple on-off valve. If the cabin needs pressure but doesn't need oxygen, then this valve is open, and the 200 psi basically backs down the oxygen system. This is a check valve here. No oxygen flows. You get nitrogen. At the point that you need oxygen, this valve closes. Then there is no 200 psi anymore. Therefore, the 100 psi provides oxygen to the regulators. So it's a very simple design.
Off the top of your head, what kind of failures did you have during qual test that really bothered you?
The regulators were produced by Carlton, and the regulators were derivatives of regulators they've been building for years. So the regulator functions really were pretty good. But the early problems we had is that the tolerance, pressure tolerance, they wandered and didn't have as good a pressure tolerance, and they did make some mods to correct that. But the more significant issues got into flow issues. their test capability was pretty limited. And when you're talking about very high flow cases, you have to do something with the gas to make the regulator think that it's in an operational environment. And so we did a lot of testing, and I'll show you that in just a second, for the high flow cases. Okay, let's see. There's a redundant system. It's not shown in this schematic, but there are two of these, just like this. This is the pressurization for the water and waste management system. You see here. Let's see, and there's a crossover to the redundant system so that you can do mix and match if you have a problem. In both systems, you can mix and match the capabilities. Also, the oxygen system provides the emergency breathing system. It also provides oxygen to the airlock for recharge of the backpack. We'll talk about that later. And I believe that's it. So for normal pressure, we have 14.7, and you have the automatic pressure regulator, basically on-off valve and the regulator. The partial pressure is controlled by the 3.2 psi, which is the solenoid that controls that. So it's a very simple system. The oxygen partial pressure does have another set point at the 8 psi. It goes down to 2.45 psi, and I'll show you that in a minute. For cabin pressure relief, the problem statement really is, why do you need relief? Well, what if one of those lines breaks? You've got 3,300 psi tankage. It's all plumbed together. The crew, God forbid, step on a line and break it, and now you've got all this nitrogen rushing in. So you don't want the cabin to explode, right? So you need a regulator, a relief valve. And the relief valve was set at 16.2. And again, that's one of the high flow cases that we ended up testing. The system was designed with 3 relief valves. Any two will do the job. That's just a redundancy philosophy. Sometimes you'll see 2 items where both of them, either one does the job. In this case, this is a very critical issue, so there is a double redundancy here. For the negative pressure protection, there's an 8 psi delta relief valve, and in fact there are 3 of those. You don't need but 2 to operate, but there are 3. This is for the return that I just showed you. If you come back, a hole in the cabin's at 8 psi, you can't reverse flow through that hole. That's not going to work. So you don't want the cabin imploding on the crew, so you've got to make up as you come in. The lower altitudes, obviously the higher pressure, you've got to get that gas back in the cabin. So that's what that's for. Okay, this is the other pressure vessel that was used as a test site. This, it was called an Environmental Test Article. Rockwell gave it that name. What they planned to do with this device when they built it was to do all the wiring runs and the plumbing runs in there. It was going to be a mock-up. It turned out they built a rather beefy tank. In fact, maybe they got one very inexpensively. I'm not sure how they ended up with it, but they got it. But they did do all the secondary structure, so it had the right shape inside. And so it turned out they didn't end up using it. They went on to other methods, and so it ended up left over in the program. And so we convinced Aaron that he ought to give it to us, and he did. This is what it looks like in Cutaway. You see here all the secondary structure. It was in boxes, but we put it all in, foamed it in so that the volume was right, so the cabin volume was essentially perfect. It had the flight deck, it had the mid deck, it had the lower deck for the environmental control system. Well, we also asked Aaron to give us the CERT hardware, which he did. So we had the CERT hardware underneath the floor, and the pressure control system we're talking about actually is on this back wall. That's a picture of it. What we did is faithfully run the lines. In fact, we even used the same line material, same fittings, same everything. So we faithfully duplicated inside this test article the volume and the geometry and the system. All the ventilation ducts you saw, all those were in place. We'll come back to it later, but you notice on the back wall of the this test facility, you notice there's an airlock hatch, and later on I'll tell you where that goes. But this is the control panel and the nitrogen system, nitrogen oxygen system. Okay, this is test data. We did some testing to see how the system worked. This was testing of basically the on-off oxygen control system. Let's see if I can walk through this simply. We're working total pressure here, oxygen partial pressure here. During this first interval, the oxygen is on. Okay? So what we're doing here, we're breathing it down, and when we hit the lower limit, so that the regulator wants to do something, when we hit that lower limit, then the oxygen partial pressure starts up because the regulator comes on. Now the total pressure is maintained because that's what the regulator is supposed to do, maintain total pressure. But as it maintains the total pressure, it's doing it with oxygen, and therefore the partial pressure is going up. When the nitrogen valve, when it's satisfied, that's enough partial pressure of oxygen, then the solenoid valve opens and you see the nitrogen come on. Now you remember the nitrogen feed was at 300 psi versus 200 psi. So there's a little jump. That's just a mechanical artifact of the regulator. If you change the inlet pressure, it regulates slightly differently because it's a balanced system. So you see a little jump there. And then during this period, the pressure is maintained, but we're breathing off the oxygen because we got the oxygen fenced off now. And then when the pressure is satisfied and the solenoid goes back the other way, then we again start the oxygen again. So the system worked quite well. If you notice, the tolerance band spec-wise was pretty wide. The system operated in a very narrow band, so we're very pleased with that. Normally that's important, not only because it shows you that you do have a good sensitive system, but you can't, mechanical hardware, electrical hardware, either one, never operates down the middle always. There's drift. So you need a little tolerance in your band here to have a decent system design. Yes, sorry.
Does this change a lot when you have the crew performing high metabolic activity?
The cabin is so large that it really doesn't know. The cycles would be, they would be different, obviously. As you consume more oxygen, you would need more oxygen. So the on-off cycle would favor longer oxygen cycles. But in the big picture, there's really not a lot of change. You might have, what was this time period? It looks like this was about three hours maybe. So that might go to 2 hours per cycle. I mean, not really very much. We're still in the atmospheric. Sorry.
Does microgravity have much effect on circulation of the air? Or not?
There is no circulation in microgravity.
Okay, so
just lays there.
So you just need, it's all from the
You
edge?
push it or it doesn't go. That's right. There is diffusion is a driving force. So if you're really, really patient, even in 0G, you can wait. But you can't stay alive that way. but yes, you do have to have ventilation. Okay, still in the atmospheric pressure and composition control. This is the emergency breathing equipment. We used plug-in face masks. There are some uses for the mask that require a carry-on bottle to give portability, but in the vehicle does have plug-in capability. The masks were purge-type masks, so you're probably not familiar much with masks, but there's a mask called a rebreather, which basically your lung power does all the work, and you only purge enough to keep the CO2 down, and you keep rebreathing. And then the purge type says every breath's a fresh breath, and you then exhale, and the gas goes out in the cabin. And that's the type that this is because the cabin needs the oxygen. I mean, it's not going anywhere bad. It's okay that it's not completely spent. It's good.
That's like a scuba mask, right? Is that a scuba valve? It's a purge type?
Don't scuba.
Oh, okay.
Sorry.
Well, I think the answer is yes. It's scuba, you take in the air and then you blow it all out. Unless, I mean, there are scuba rebreathing systems, but they're the typical scuba gear is not.
Okay. Rather than raising your hand, if you make a noise of some kind, I'm sorry, I don't mean to ignore you. The mask can be used in a contaminated environment, and the mask can be used if the concentration of O2 is low to give you a better oxygen level. This is the 8 psi test that we did, actually a series of tests, but this is data from one. As you see, we started up in the 14.7 range. We simulated the hole. The pressure immediately starts down. The partial pressure of oxygen we let degrade to about the 2.2 range. This is a different set point. You remember I told you on the oxygen sensors we have 2 set points. This is the second set point. And so we have the lower oxygen partial pressure. The system came down. The 8 psi regulator, which is always online, captured the pressure decay, caught it. The solenoid valve popped back and forth to keep the oxygen okay, because we're losing now. We're going out this half-inch hole. And the system worked just fine. This did have the crew on the masks, because that's livable. You can live there, but the mask is a better environment. So this is a mask case. Okay. This was a requirement that came on later. The design is the design now. The vehicle exists. So we have to now operate that vehicle with accommodations for whatever operationally we want to do with it. And a new requirement developed and was imposed on the vehicle, and that requirement had to do with the spacesuit, with EVA operation. The shuttle spacesuits are basically 100% O2, and the classical way of going EVA from a sea level environment was a 4-hour pre-breathe, actually as much as 6 hours depending on the how conservative the medics were at the time. That number varied around some to prevent bends. But it was determined that if you acclimatized at 9 psi for about 12 hours, then you only required a really short pre-breathe, and the suit-up time, which gave you 30 to 40 minutes, actually gave you sort of a free tune-up to your pre-breathe as part of your suit-up operation. And so that was viewed as a much better way to do EVAs than the previous way. The masks are useful, but they're not very comfortable. So if you have to keep them on for a long period of time, they're not very comfortable at all. Also, the medics were very concerned about mask leakage, that if there was any inflow, nitrogen inflow, that could break the pre-breathe. But our system isn't designed for 9. We have a 14.7 and an 8, but we don't have a 9. So we needed a manual procedure. But before that could be accepted, there were some issues that had to be evaluated, and we had to do testing on each of these issues. The first is the flow rate acceptability at 9 psi. Obviously, the less dense gas, you're not going to get the same mass flow rate. And we had to make sure that that ventilation was going to be adequate, and testing proved that it was. The next is the thermal acceptability. There are really 2 aspects to this. One is the fan itself is cooled by the environment, so if the environment doesn't provide as much cooling, the fan itself could overheat. Also, the electronic equipment, some of which is air-cooled, the less dense gas could be a problem there. It turned out that could be controlled with load control. They could offload power and make that acceptable. The CO2 performance at 9 psi, we needed to make sure that was okay. It turned out that, of course, the 8 psi case, we don't care about the lithium hydroxide. The purge flow is so great, there is no CO2 problem. But at 9 psi for 12 hours, you have to get performance out of the lithium hydroxide. So we checked that, and that worked out fine. And the last item was the ventilation adequacy. We do have a press and depress. You've got to come down to 9, and you've got to go back, and both of those adjust the gas mixture. And so we wanted to prove that that was okay. And so we went to the facility that we were talking about and ran this profile. Now, this profile was created by our, yes?
Originally you said a lot of the shuttle equipment was designed according to this, you didn't want to change that. But now that you've brought EVAs, you lower the pressure, does that affect equipment?
Well, that's what I just said. Yes, it does. The air-cooled equipment is going to run hot. So if you want to cool that equipment, it'll become a little clearer later, but the equipment is in bays, equipment bays, and so if with the less dense gas, you need to have some of that equipment turned off so that the cooling that is available is adequate. So you do load control, get rid of some of the electronics, and therefore the air that's left, or the atmosphere that's left, can cool the equipment.
And then when do you increase the pressure back to normal after the EVA?
After the 12 hours. No, actually it's before the EVA. Well, I'm not sure what they do now. I think right now,
when you're all finished with your EVAs, then you bring the cabin back. Because typically you do multiple EVAs, and so from one day to the next you just keep the cabin at, and actually we use 10.2 now, I think,
Yes.
rather than 9.
right.
But I think you had to certify it for 9. Right?
This was an early certification for 9. Okay. Yes.
Would it have been easier to simply design the whole system for 9 from the beginning if you had new?
Well, this was not a shuttle requirement. This was an operational requirement that occurred after the shuttle specifications were set. You're correct.
Would you have had
If we knew it ahead of time, yes.
it would have been much easier to do it all for 9 PSIs.
Exactly. Exactly. It would have just been a third condition. But as Jeff pointed out, we changed our mind. The first was 9, and now we're at 10.2. So we don't, we're not consistent. As we learn, we change our mind, and the 10.2 was selected later. Okay, our mission operations people that do the crew timelining and all, they created this procedure, and so we tested it. This has a simple depress cycle. You come from 14.7, you hesitate at about 11 and replenish the oxygen. You do that twice. You then do manual control down at the 9 PSI level. You notice the oxygen partial pressure here is always maintained by these adjustments, and also during the manual period you select which you want. And then when you come back, the procedure was to increase the nitrogen and then finish the top off with oxygen. That was thought to be completely acceptable because the oxygen level at this point is completely viable, and so doing the nitrogen first and topping it off with oxygen was thought to be an acceptable way to operate. So we did the test, and this is what happened. We were all nice and comfortable with our oxygen partial pressure, and you see the area next to where we were repressing, we depleted the oxygen substantially, and the mid-deck and even the flight deck, we depleted the oxygen. And I've only shown you half the data, so if you look at the rest of the data, you see where the oxygen went. These equipment bays that I mentioned earlier, the avionics bays and other equipment bays, are basically isolated volumes from the cabin. So as the pressure comes up, what you're doing is you're pressurizing these areas with cabin gas, which is oxygen and nitrogen. You're pressurizing these areas with nitrogen only. So basically you're depleting the partial pressure here, you're increasing the partial pressure here. You remember partial pressure, you just count the molecules. That's all you have to do. So basically we're putting more oxygen molecules here, and we're taking them out of these areas, and therefore they're going down. So we developed these. This is just a picture of one of the bays. You see all the empty space around the equipment. It's where the gas is. So we came up with an alternate procedure, which is to simultaneously put the oxygen and nitrogen in together. And of course there's the 9 back to 14.7. And you notice that solved the problem. There's still some dip at the supply area because the mixture's lean. We need from 9 to 14.7, 5.7 psi total pressure increase, but we only need 2.5 up to 3.2 oxygen. So this is it's a mixture, but it's a lean mixture. So there's still some slight loss, but the only area that came under an issue is near the inlet where the O2 N2 supply panel is, and of course you can just avoid that area.
Well, I should say that area happens to be right around the bathroom. And so before we repressurize the shuttle, the commander would, anybody who has to use the bathroom, use it now, because, you know, for about 10-15 minutes while we're repressurizing, it's off limits.
Okay, the next item. This is the water and waste management area. This is one of the 6 items. We have potable and wastewater inventory management. We're continually producing potable water, as you know, and wastewater. We have to dump them, we have to use them, so that is part of the requirement of this system. We have to store water for drinking, food prep. Wastewater storage has to be dumped to space, commode and urinal for human waste collection, and we provide water for an evaporative heat sink, which we'll talk about later, called the flash evaporator. Yes?
This is an outstanding example of systems engineering, this total system that Walt's talking about. You can really see the interaction between all the systems and the spacecraft. It really is a systems engineering problem.
Potable water, we take all the fuel cell byproduct water and use it, so it's basically an effluent to the power system. We do have launch storage capability for water, and we do provide sterilization. The sterilization is iodine. We started out designing a silver ion system. It turned out that we had manufacturing problems, and the company ended up going out of business, and so we reverted to iodine. The lunar module used iodine. Wastewater, the condensate from the cabin humidity control, and a urine pre-treat. The urine has to be pre-treated to bind the urea. If you don't, you get a lot of ammonia. It uses a chemical called oxone, O-X-Z-O-N-E, I think. It's an acid. I'm not really sure what it is. Okay, this is where the system's located. This is one of the simpler schematics. The water tanks here. The water comes from the fuel cell, as I said. It goes, by the way, the delivery is about 150 psi, and 150 degrees and 60 psi. So there is a lot of hydrogen dissolved in the water. The water is collected in the fuel cells on the hydrogen side. So there's a lot of hydrogen. So there's a hydrogen separator here. Otherwise, your tanks would end up full of hydrogen, which is what you don't want. You want water in the tanks. So the hydrogen separator is a silver palladium metal. It's catalyzed. It's basically porous to hydrogen, but not to water. If you expose the backside to the vacuum, pulls the hydrogen off, and the water goes through just fine.
I will say that there still is a rather high gas content in the water that you drink, and that gas, of course, evolves once it gets inside your stomach with predictable results.
Yes. In fact, all sorts of systems that Jeff could explain. They have slinger systems and all sorts of systems to get separation, because it's not really possible to get all the gas out of the water. Okay, there's a dump system. There's a potable dump to vacuum, a waste dump to vacuum. There's also a vacuum vent, which I'll show you what that's all about. And then the flash evaporator that I mentioned, and I'll mention more later, is in the back of the vehicle, and it has a redundant water feed system, both sides. Okay, this is the schematic. Start at the same place. Water from the fuel cells goes through the hydrogen separator, and then into this bank of tanks. The tanks are pressurized on their metal bellows tanks. On the back side of the bellows is nitrogen. On the forward side, of course, is the potable water. There is a hydrophobic filter on each side, on the downside of each tank. If a bellows were to leak, you don't want water into your nitrogen system, so this is a filter to prevent that. I mentioned the twin flash evaporator feeds. There they are. This is the dump nozzle here. The potable water system provides water to the crew, so there's a regular water interface and a chilled water interface here. I believe that's it.
Well, I remember more problems with the Apollo water than I did with shuttle water. Right or wrong?
I don't have those sorted mentally. I'm sorry. I don't remember. I'm not sure. Yes.
Yes. I don't know, the slinger, where do we use the slinger? Do we use the slinger Apollo or shuttle?
Maybe that was an Apollo.
No, we had them in the shuttle.
I get confused too.
Basically, that means you put your water into a plastic bag, and now you can actually sling it around like so, and so the water will go to the outside and the gas is on the inside, so that actually separates, and then you can squeeze the gas out through a valve.
Okay, on-orbit trash storage, there is an overboard bleed for odor control. It's a very small overboard bleed to vacuum. And the human solid waste collection and storage, that's also vacuum dried and stabilized. This is a waste management picture. The subject we're just talking about is the vacuum vent. The vacuum vent does vent the Commode area where the feces are. That vent also provides a vent for the water separator. It also provides a vent for airlock depress for EVA. So this is the vacuum system. The urine is collected and trained in a liquid, well, let's say that differently. The urine is, after it's been separated from the gas stream, is stored in a waste tank, as is the humidity from the cabin thermal, the atmospheric revitalization system. And then that is pressurized from the pressure and composition control system, and it's dumped overboard. This water is not used for anything. It's basically dumped just to do inventory management. The next picture explains a little better about the Commode and the urinal themselves. The urinal originally had a unisex interface cup. It turned out that didn't work very well, and so later flights there was a custom male-female, and later there was even some more customizing for the crew, I believe, but I don't have the details on that. But the urinal itself, obviously, for urination, there needs to be some way to make the urine go where you want it to go, and those were done in fan separators. So there is gas pulled in the cup, and in training the urine then comes down and goes through the separators. This is also a centrifugal type separator, and then that's sent to the head that's created here, then puts that wastewater urine in the waste system. The EMU spacesuit, it also has a condensate drain after each EVA, and it also goes through the same system and into the waste tank. The Commode is basically, there's a seat. The seat has a small opening. The Commode itself is basically a cylinder or a tub, and there's a slinger in the bottom. So the slinger basically distributes the paper and the fecal matter on the outside wall in a thin layer. The vacuum then can dry that so that it deactivates it, so it does not end up either any odor or creating any kind of bacteriological issues. But the entrainment of the fecal material so that it, in fact, hits the slinger is done with an airflow. The airflow comes in around the seat itself. That requires a good contact with the seat. It also requires positioning. It turned out that positioning turned out to be an early issue, or reliable positioning. And so a trainer was put together that had a camera here. And the trainer, I might add, was discreetly located in a non-observable place, so that it could be used in privacy, the comings and goings, and also the use of the facility itself.
And they told us that it was not hooked up to a tape recorder.
But anyway, I think that...
Just to elaborate on that, basically the problem, it really is a rather small opening, and it just doesn't feel natural to know where to put yourself down. And it actually did lead to significant messes on orbit. I won't go into any more detail, but the idea is that you would position yourself the way you thought it should be, and then you turn on the lights, and there's a TV screen in front of you. I'm not making this up. So that you could see how close you are to the bullseye. Enough said.
Okay. The cabin thermal control is another one of the subsystem elements. It's a circulating liquid cooling system. It provides the heat sink for the atmosphere itself. It also provides the ability to reject that heat to the spacecraft cooling system, because you got to get rid of it out of the cabin. It had some avionics cold plates, some air-cooled avionics, support the crew in the airlock, and the potable water chiller. This is the location. You notice the avionics bays are listed here with their little circulation systems. The liquid system then services each of those, the chiller, the condensing heat exchanger. And this is the place that the cabin system connects to the spacecraft system, is on the aft bulkhead right here. We'll see the other half of this system in a little bit. This is schematic. It's very complicated looking, but it's fairly simple. Let me show you the air piece first. Look at the black lines. There's the twin fans, goes through the air-cooled avionics, through the heat exchanger to get rid of the heat. There are some cold-plated avionics in each bay, so you take care of the cold-plated and the air-cooled in this bay, in this bay, and in this bay. So now you've got all the electronics taken care of. That coolant loop then has to service, I should have started this up at the pump. Sorry about that. Here's the pump. Come down. Also takes care of the forward and overhead window mounts around the window for thermal control, and the hatch. It's just a way to keep those thermally stabilized. Back in the early flights, we had something called DFI, Development Flight Instrumentation. It was a special instrumentation package. It was also liquid cooled. And then this is the heat exchanger to the spacecraft system. It's a Freon system. This is where the main heat's rejected, right here. So on the other side of this, you've got cool liquid. Turns out this is water. We go through the liquid cooling garment, which is the spacesuit cooling garment, the water chiller, go through the cabin heat exchanger to cool the cabin and condense the water out, and then back to the pump. I failed to mention the IMU. It has triply redundant fans, pulls air through it, and that's also cooled by this gas stream. So anyway, this is the cabin thermal control system. These functions, I just said each one of them. I won't repeat them. Cabin circulating liquid cooling loop. As I mentioned, water is the coolant. Water is actually a very good coolant. And if you have any requirements that push you that way and you're designing thermal control systems, you like water. Water is completely non-toxic, so it can be around the crew. Leaks don't make any difference. Has a very high CP. It's a really good fluid. Problem with water is freezing. You don't want to freeze it, and you don't want to get it so hot that it turns into steam. But if you can stay within the boundaries, it's a good fluid, and that's what this is. Redundant pumps, I showed you that on the schematic. The liquid gas heat exchanger, showed you that before. Cold plates for electronic cooling, and the window hatch mount. The circulating gases that I mentioned for the avionics, the cabin gas was used as a coolant. You saw the redundant fans and the doubly redundant fans. I mentioned earlier, and someone commented on it, that the promise early on was the shuttle could be a less expensive development activity if we used off-the-shelf avionics, the kind that aircraft use. And that's a good promise. It turned out that that's not a very good, not as good, a solution for thermal control as liquid cooled. Liquid cooled is a much more efficient way of providing a heat sink to electrical equipment. When you blow the cabin gas through it, then you end up with the problems of if you change the pressure in the cabin, which we've talked about, that can affect cooling. It's also, you have to put out a lot more power. You have to blow a lot more gas than you do power to move the liquid around. So it's not a very good thermal solution. And actually, the promise of less expensive avionics I don't think was actually fulfilled, although that's somebody else's topic and not mine, because I think everything was pretty well custom. So it did potentially complicate the thermal control system for a good goal, and how well that goal was met, somebody else will have to speak for. Another one of the subsystem elements, the spacecraft.
Why don't we usually take a minute break, and then we're about halfway through, so why don't we take our 2 minutes now, and then we'll pick right back up.
Everybody, yes.
I had one quick question, just about what you were saying before, the electronics that are cooled by air flow versus, did you say would probably
From an engineering standpoint, it's much better to cool with liquid. So if you use cold plates, it's much more efficient. You get a good, reliable heat sink, and you can then design your thermal conduction paths so that out of the avionics box you make sure the heat goes to the cold plate, and use a lot less power. You can pump water a lot more efficiently for the cooling capability than you can pump gas.
So is that what actually happens on the shuttle now, or do you have a mixture of both air cooled and both?
I guess following on to that, even like how much do you have to change in order to just water?
Let me finish this. You notice here, this is the air-cooled part of the loop, and here are the cold plates.
Let's get the class back.
Thank you very much. I'm sorry, did you see what I was pointing at here? Yeah, and this is one bay, and they have both cold plates and the air-cooled here, here, and here. There they are. Of course, when you go outside the vehicle, there's no more air, so all the external equipment's cold-plated. Was there another question?
Yes, sir. I was just saying, what kind of design changes would you have to make in order to go strictly to completely liquid-cooled electronics?
Well, if you're trying to use off-the-shelf, and it's air-cooled already, there's a cabinet right there full of it. Right. If it's air-cooled already, then you have to stay with that concept. If you're custom designing, then from the very beginning you say, I'm custom designing this to be liquid-cooled, and then the internal design is such that there are conduction paths to the base plate so that it can be cooled. Okay, let's see if I can...
Because previous to that, all of our spacecraft were Apollo was liquid.
Yes.
Because you had to be able to take those spacecraft down to vacuum.
Right. We evacuated the cabin both in the command module and the lunar module. And Gemini too. Okay, here we are. This is the spacecraft active thermal control system. This is the vehicle level, so that we're now, even though we're still under this ETCLSS, we're not talking the classical environmental control anymore. This is a bigger picture. Also, the reason the word active is stuck in here was a leftover from previous programs too. For example, on Apollo, we had several heat rejection systems, not a single one. And we also did a lot of passive thermal control on Apollo. We had a mission mode called barbecue, which is basically you roll the vehicle very slowly, so you normalize the environment. If you leave the same side toward the sun all the way to the moon, that side gets really hot. So this is the active system to get away from heaters and or vehicle level control. Okay, there's an on orbit. We have a radiative heat sink. We also have an evaporative heat sink on orbit. During ascent entry, we have two heat sinks, both of which are evaporative. We have a circulating liquid system. We take heat from the cabin, from the fuel cells, hydraulics, all the cold plate avionics, electronics, and payloads. We do cooling for payloads. So all of these are the functions of the active thermal control system. I don't know why. There it is. This, as you notice, is a lot busier than some of the others have been. You notice the radiators here on the sidewall. This is the doors. When closed up, there are no radiators. When open, the underside of the payload bay doors are your radiators, and it's on both sides, obviously. That same heat exchanger that I showed you before that interfaces with the cabin is right here. So the cabin load is dumped there. Fuel cell load is dumped here. The fluid is a Freon 21. There's a Freon 21 pump package. The payload heat exchanger is here, I believe. Mid-body cold plates, aft cold plates. Each radiator side has its own flow control system. The evaporative heat sinks, one is the flash evaporator that I've shown you a couple of times before. I'll describe a little better in a minute, is here. It uses water. There's an ammonia boiler here that is also an evaporative heat sink. And when we're on the ground, there's a GSE connector for GSE heat sink.
Analytical work was done for heat balance, to understand that.
More than you would ever know. In fact, this is the most complicated integrated thermal test ever run at JSC, and I'll show you a picture of it in a minute. We actually tested all of that together, and it all had to work together, and it gets worse as we go along. I'll show you all the integration factors as we go along, but it changes from mission mode to mission mode. It changes within mission modes as to how this system works, and I'll try to describe that. Okay, so this sort of gives you the feel. Now, keep in mind geometry is going to play an effect here. As to how you plumb the system up.
So all of Freon is running through all of those lines there to the radiators?
Right. Okay. It'll be a little clearer in a minute. Okay. This is a schematic. Let's start at the radiators. On a good day, this is doing the job for you. All the radiators are getting you nice, cool liquid. The radiator uses a bypass system, so that you see the bypass around the radiators. It's good to remind yourselves that the heat load can be tremendously different in high level mission phases. A lot of electronics, a lot of crew activity, a lot of the vehicle is alive and pumping out the power and therefore pumping out the heat. If you ever did one of those 28-day missions we talked about, which was a spec requirement, you can imagine this vehicle is almost quiescent. It's doing very little. You're trying to lengthen the mission, so you're doing hopefully experiments or something in Space Lab or Space Lab. You're doing something else. You're not really, the vehicle is not working for you very hard.
Just as an example, we have 5 computers, and we use all 5 during ascent and entry of the active phases for safety. But once you're on orbit, when you have a long mission like that, you actually power down all but 2 of the computers. That's just it. And there's a lot of other systems which you power down, and that way you're limited in many missions by the electrical energy, which is limited by the amount of hydrogen and oxygen you can carry for your fuel cells. So by powering down, you extend your mission, and of course you'll also reduce the heat load.
And when you reduce the heat load, you've got to find some way to make that same radiator work for you at a very low heat load. So it has the capability of getting rid of a lot of heat. If you don't want it to get rid of that much heat because you don't have it, then you have to go to a bypass system. Anyway, the next thing in the loop is the GSE heat exchanger. So on the ground, you don't have radiators working, so you use the GSE heat exchanger. Then there's the ammonia boiler. When you re-enter, the ammonia boiler gives you the ability to operate with an evaporative heat sink prior to the connection of the GSE, and so it's part of the thermal control system. The next is the flash evaporator, and you notice there are 2 flash chambers here. One's called the high load, one's called the topper, and I'll talk about that a little more later. Then the nice cool liquid, however it was cooled, all these cool it, however it was cooled is then available for the vehicle, and there is one more little heat load, and that's that cryogenic oxygen that we're bringing in. We also warm it up with this coolant loop. So the flow then goes to the aft cold plates, and then the flow also goes to the cabin heat exchanger and the payload heat exchanger. You notice these are either or, and that's because sometimes you don't even have a payload heat exchanger use, so you don't use it. Sometimes you have a lot of use for it, and maybe, for example, a Space Hab kind of an arrangement, you wouldn't be in the cabin as much, so you can divert that. So it allows you to use the capacity in either of two places here. Then you come on down and come through your pumping package. There's redundant pumps. Then you go to the fuel cell heat exchanger, because now you've used the cold fluid up, and so the fuel cell can stand to warmer temperatures. Also some cold plates. Now it might have occurred to me, why did we waste our nice cold fluid on these cold plates? Why don't we put those cold plates down here so we could have had more cold fluid for our cabin heat exchangers? And the answer is geometry. Those are way in the back. The cabin is in the front. So after you've come forward from the flash evaporator, which is in the back, to the cabin, you don't want to go back to pick this up. So you wouldn't want to have to go back to the back of the vehicle and then back forward again. So this is a geometry problem. So we have cold plates here. We also have cold plates here. We come forward. There's the hydraulics heat exchanger is the last thing on the loop, and then back to the radiators. We'll talk about that a little more. The functions of the active thermal control system: collect the waste energy from all the systems, we just talked about that, and reject it radiatively to space. That's our first choice. Our first choice is to use the radiators. It turns out that the radiators in some heat load environments don't do the job. You have a high load and a bad environment, you can't get rid of all the heat. Also, we're producing a lot of water, so something's constructive has to be done with this water. The fuel cells are pumping it out because every time you make a kilowatt, you've got more water to use. So we decided to augment the space radiators with the evaporative heat sink at these high load cases. This gives us an ability to accept a radiator system that can't really do the job by itself, but make it completely adequate for some of the low heat load cases. But in the high heat load cases, then it's augmented by water. Now, when you want to get rid of water and you don't have some of this bad environment, you can actually throttle the radiators down. And if you throttle them down, then you force the evaporative heat sink to come online and do the job for you. So in other words, you change the set point on the radiator. Normally we use 40 degrees set point. If you change it to 56 degrees and let the water take you from 56 back down to 40, then you artificially get rid of water. So it's a good water dump system. During ascent over 100,000 feet, we use a water boiler, a flash evaporator, not a water boiler. That's a Freudian slip, I guess. The Apollo had what's called a water boiler. It was a nightmare. We said never will we do that again, so we ended up with a different design for the shuttle. The re-entry system below 100,000 feet is ammonia. It'll carry you all the way to the ground and on the ground until you get to GSE. Water won't carry you because water won't evaporate less than 100,000 feet, but the ammonia will. So that's the reason it's there. Okay, let's talk about the radiators themselves. The two payload bay doors are a mirror image of each other. So there are radiators on each side that are exactly mirror image. I don't know what happened there. Anyway, this is supposed to say that the radiators on these two sides are mounted in or plumbed in two separate cooling loops. The reason for that is if you ran, there's always a redundant loop, obviously. You have to be able to take a failure and still have a good system. If you run both loops through both radiator sides and you took some sort of a collision hit, then you could wipe out both of your cooling loops in one hit. And so that's unacceptable. So by plumbing the systems up with mirror image radiator systems on different loops, then you can still use the capacity together, but if you lose one side, you still have half your capacity left, and plus you have your evaporative heat sinks to make up the difference. So we can survive with a panel, a door out. I mentioned the dual set points before, also mentioned the bypass thermal control. I mentioned the dual set points, 40 and 56. 40 is our normal. If you're trying to burn up some water, you go to 56 and you use the difference in water. The radiators, we have two different kinds of radiators. We have the single-sided, they're on the back of the vehicle, and some two-sided ones on the front of the vehicle. The reason for that is when you open the door, you expose the underside of the door. If you have radiators on the underside of the door, then you've exposed your radiators. But if you lift the radiator panel off the door, because the doors go way down, like gullwing, if you lift the panel off the door, then you can see the underside. It's not as good, don't get a full view of the heavens, but it does get rid of heat. And so we needed that extra capacity. So on the front four panels, they're the two-sided, and on the back four, they're single-sided. The radiators themselves are made out of a honeycomb aluminum structure. The tubes were embedded in the structure so that the surface was smooth, and that was because we wanted to use a silver Teflon tape for our thermal control coating. For previous vehicles, we'd always painted the radiators, painted them white. If you look at the Alpha, Epsilon white paint, it's pretty good. It's about, I think Apollo was 0.18 Alpha and Epsilon about 0.92. It's pretty good. The market had moved along. Technology had advanced, and there was now the silver Teflon out there. And what the silver Teflon does is the silver gives you the reflection, which is good, and the Teflon gives you the radiation, which is good. So you get the best of both worlds. So silver Teflon was about 0.05 Epsilon and about 0.88, 0.9, something like that. So you lost a slight amount in Epsilon and gained a lot in Alpha. So basically you could ignore the sun, which is what you'd like to do, is ignore the sun. It turned out the silver Teflon had some issues. We tested the radiators. The radiator was not a slam dunk. With 8 panels, 4 of which are two-sided, effectively you have 12 panels. You have fluid going through those in parallel tubes. You're trying to guarantee that the fluid all goes where it's supposed to go, and therefore the viscosity of Freon, which is very low, analytically said it was all right, but we wanted some testing to prove it. So we did test the entire radiator system, and in that test, all the silver Teflon fell off. So it said it's a really good thermal coating, but it doesn't seem to be very practical. It turned out that the problem was adhesive. So we did a little adhesive work, and the materials people came up with a permacell that worked perfectly. They've never come off again. In fact, we get 10, 12 years out of the radiators. We don't, lots of time. The problem that the permacell couldn't solve was beneath the tape you could get very small little outgassing of the materials, but almost all materials outgas some. So basically it would put bubbles underneath the tape. So we went to a perforated. So there are millions of little holes in this tape. And it's placed on the vehicle, and it stayed on just fine. It wasn't very long, though, that people began to worry about the focusing of this silver, that the doors are curved upward, and so there's a focal point there that is a very, very hot point. And it was concerned that that's really not a good thing to have. So if we could make the surface less specular and more diffuse without losing the alpha and epsilon, we'd have a better design. And so they dimpled it. So now we have permacell, dimpled, perforated silver Teflon tape. Works great. Okay. The flash evaporator. This is water is the flash evaporator's evaporant. This was a brand new design. The water boiler on Apollo was no good. It was a problem. The flash evaporator is a very simple concept. You have a chamber. You run your coolant around the chamber that you want to be cooled, and you spray water on the walls of the chamber. And if the pressures are all right, the water will flash. You won't get liquid. It'll go straight to, you won't get ice. It'll go straight to steam. Steam will go overboard, and it'll all be wonderful. And if you can convince a program manager of that, good luck. But anyway, the way to convince the program manager is to show them good test data. So during the development, we developed this process of spraying the walls and not getting water carryover, which will obviously freeze up your steam duct, which you don't want. But as the design evolved, we had to get more sophisticated because we needed this flash evaporator to burn up the extra water that when we didn't need the fuel cell water. And we did that with that 40 to 56 set point. And so we needed a small evaporator that could handle that. So it was called the topper. So it tops off the radiator. But when the doors are closed and there's nothing else to get rid of your heat, now you need a loss of capacity. And so the second chamber was the high load chamber. Together, they do the whole job. When the radiators are working, only the topper. So you can come home with this system functional and make it home. It turns out we never did freeze up the steam duct, so that part was good. It turns out that we had some freezing in the chamber. And in fact, we had to develop a process that acknowledged that that could occur and how would we flush it. It's called flushing. And so we did develop a process, and it has never failed. The flushing process always works. And we have had on several occasions, I probably can't count them for you, but 4 or 5 times maybe over the shuttle flights, we've had some freezing inside the cavities. Okay, there's a non-propulsive overboard vent. That was the one going out both sides for the topper because it could be used for very long times during the mission, and you might be pointing or whatever you might be doing. But when you're coming home, the high load is just a big out the side of the vehicle type duct. The ammonia boiler, its heat sink is ammonia. As I mentioned before, it evaporates all the way to the ground where the water won't. The redundant boilers here, up here there are no redundant boilers. These two chambers have redundant everything. They have redundant feed water systems, redundant control systems, redundant spray nozzles, redundant everything. But the chamber is a chamber. You get what you get. There are redundant boilers, is the way the ammonia boiler gets its redundancy. It's utilized, or was designed to be utilized during entry and on the runway until cooling's available. It turns out that we don't do that anymore. It turns out operationally, we learned that if we cold soak the radiators before we shut the doors and then bypass them and come home on the flash evaporator, that there's a lot of heat capacity still left in those radiators, a lot of fluid out there, and it's cold. And so we can actually go all the way to wheel stop on the radiator. And so at 175,000 feet, we start flowing the radiator, but 100,000 feet, the flash evaporator is off, and we cold soak all the way home, and after wheel stop, the ammonia boiler cranks up. I mentioned the Freon 21, the low viscosity. We've gotten excellent performance out of that. The low viscosity is really, really important, as much parallelism as we have. I didn't really give you the numbers. In the single panels, we have 26 tubes. In the two-sided panels, I believe there are 66 tubes. Lots of tubes, lots of parallelism. So it's awfully easy to get flow instability in a thermal system like that. But the Freon loop does great. We have redundant pumps, all liquid heat exchangers and cold plates. This is that chamber that I told you. If you can look right down here, this is a people right here. One person. This, in fact, there's a radiator panel. This was during build-up. Twice we tested the flash evaporator in this environment, once as part of the integrated system with all the radiators, and once by itself. And twice we tested the radiators, one as part of the integrated system and once by themselves. So we did essentially 3 tests, large tests, and the one that had the entire system in it, had all the cold plates, it had everything in it, is, I said, the most sophisticated thermal test we've ever done at JSC. And it proved that the system could work. It also proved that we had to tune the flash evaporator nozzle because it was wrong. But we did get the data, we did prove it was wrong, and we got it remachined. Machined out of Columbium. Somebody else will have to answer why. And so it was a problem for Aaron to go get us another one, but but it fixed it, and it was successful.
Well, that chamber was built actually for Apollo, right?
Yes. It'll take a stacked, you can have a command module and a service module and a stacked configuration inside that chamber. And it had solar and full vacuum.
We actually put Ben in there.
Yes. It was a manned chamber then. It's not now. After Apollo Soyuz, it hasn't been manned since then. But it's still available for testing, but it's not manned. It has a sister chamber 100 feet that way, where all of the EVA testing is done.
It's a good example, I think, of how the shuttle program built on a lot of Apollo. Same thing at the Cape, where a lot of the launch hardware was adapted. Because the shuttle program, you heard about the budgetary constraints. The shuttle program never could have afforded to build something like that. But luckily, a lot of this equipment was built during Apollo when money was much more available.
Okay, if you've been keeping count, we're getting toward the end here. I did want to mention before we left the main orbiter systems that there was some rotating equipment life testing that we did for the program. The equipment we're talking about here is the cabin fan, the water gas separators, the avionics bay fans, cabin coolant, and the vehicle coolant pumps. The life requirement was 100 missions, and that was calculated by somebody to be 20,000 hours. So if you could show 20,000 hours of successful operation, you had the design life of the hardware. We set up a laboratory to run the equipment. It was obviously a low maintenance lab. We collected data and checked in the room occasionally to see that everything was all right. It turned out that all the equipment passed the 20,000 hour requirement. We did learn something, though, that some of that stuff was so noisy. Oh, it was noisy. So there was some work done on some muffling, but the hardware itself was all good. Okay, we are at the end. Yes?
What are the noise requirements for machinery?
Yes, there was a cabin noise spec, and yes, it had to be met. And I don't remember how it was met. Whether they'd put
mufflers on some of the equipment.
maybe some insulation inside of the ducting. I'm not sure.
We have time. I'll tell a little anecdote here. We were out chaired the change control board. And the doctors, the medical organization, came to see me and said that the cabin was very, very noisy, and it was going to really do a detriment to the astronauts. And it was very expensive and very, in terms of dollars and weight, to really get the cabin, all the cabin fans and everything, cabin environment down to the level they wanted. So I thought for a moment, and I said, well, I go out to California a lot. I go out to Rockwell, and I stay in the motels that are on the Los Angeles freeway. And I said, you don't seem to be worried about me, my ears, in staying on those freeways and not being able to sleep and having all that noise. And the doctors looked at me for a moment and says, well, you're already deaf. And I said, what did you say? So, but we did have to make some modifications of it to actually reduce the noise. Let me interject one item. I think somebody asked the issue about the IMU. We decided to pick the IMU off the shelves, and it was air-cooled. To really do it right, if we would have done it right, we would have picked an IMU which was compatible with liquid cooling rather than or redesign it. But we decided to stick with the IMU that was air-cooled. And whether that was the right decision to make, I don't know. It seemed like it was, because I think we've only had one problem with an IMU. I don't think we've had many problems with the IMU. But that's a little anecdote that I thought.
That's a program manager's trade. Probably the air-cooled IMU was a less expensive option. It might have cost a little in terms of thermal efficiency, but that's only energy, power, and power was available. So it was a good trade-off. Okay, this is the last of the subsystem areas. This is the EVA airlock support. The environmental thermal control and life support system does support the airlock. It maintains the cabin pressure and composition during the airlock repress and depress. This is really a requirement back on the ARS and the pressure and composition control system, because airlock use basically dumps cabin gas and then you repress the airlock. So it's a requirement that you cannot upset the cabin while you're doing the EVA function. We also provide the service and cooling umbilical. If you have any kind of mental picture of being in the airlock, the crew is connected with cooling and oxygen through an umbilical, so they don't use the consumables in their spacesuit and backpack. And so that's provided by the ETCLSS. Heat rejection, the crew wears a liquid cooling garment, and the cooling for that is done by the vehicle until you go EVA, of course. Then the recharge. We supply the backpack O2 recharge from the cryo, the 900 PSI cryo. We supply the water to recharge for the sublimator. The EMU uses the EMU's NASA's overrun with acronyms. EMU is Extravehicular Mobility Unit, which means nothing either. Spacesuit and backpack. So the spacesuit and backpack uses an evaporative heat sink, and it uses a sublimator. And the idea there is it's a device that exposes a layer of ice to space, and then it sublimates, and you get your cooling from that, as opposed to putting liquid water on a surface and flashing it. But anyway, that has to be serviced, and so that water is provided from the system. And then the condensate that the crew brings back off an EVA, that's a sweaty job. That condensate goes back into the system. So the airlock support is another part of this system. In fact, that's the 6th part, so we are through. This is a picture of the airlock. Not really the airlock. This is the test chamber that we built to put the equipment in. You notice it has the right hatch in it, and if you can recall back an hour and a half ago, showed you a picture where there was this hatch basically on the other side of the back side of the test chamber. We hooked those together because, as I said, as you depress and repress the airlock, it affects the cabin. So we needed a test environment that had both those simultaneously. But the difference is this has to go all the way to vacuum. So we connected this to our vacuum system, and when the crew is inside this, it's a manned vacuum test. And when the crew is inside the other test chamber, it's basically sea level, or at most 8 psi would be the lowest it would ever be. And I think the last picture is a spacesuit inside the airlock, and this is just a little cutaway showing the airlock. This was mounted on the back of that chamber you saw earlier.
So if
okay.
you bring that picture back, I'll talk to that for just a minute, because and then we'll have some questions. But before every flight, one of the things that we do is that every EVA crew member takes his or her spacesuit into that EVA test chamber, into the airlock test chamber. So you actually get a chance to take your own suit down to vacuum. And particularly before you do your very first EVA, it's really a confidence builder, because the physical sensations that you get in a suit, remember you're at about 4 psi pure oxygen environment, and your body, the inside of your mouth, feels a little different. There's funny sounds with the fans inside the suit. The sorts of things you don't want to experience the first time when you actually go outside into space. It's much better to do it here in a controlled environment where, if there's a problem, actually you're supported because of the weight of the suit. Doesn't look like there's anybody in this suit. No. So, but when you're in the suit, you're actually supported by a cable to the ceiling of the chamber, which is on quick release bolts. So
Picture to the left there.
yeah, okay, right. So you're suspended up here, and if you ever have a problem, they can release this, repressurize the chamber within about 30 seconds. I think that's the limit for a man-rated chamber. You got to be able to repress in about 30 seconds, and then just lift you out, suit and all, from the top, and get you out of your suit and get you to the medics. So
This is just an inverted bell jar. The hatch is not sealed. When you depress, it just like pulls it down, seals due to the pressure difference.
So, yet another.
You just lift the top off.
Yet another example of the extensive testing that we go through before every mission. So,
I might add one more thing I forgot actually to add earlier, is that the man rating is a term used in manned spacecraft, which means that you've specifically tested it and said that its design is worthy of supporting a human. The airlock had to provide that function. So Aaron was faced with man rating the airlock, and man test capability is very scarce, very scarce. In fact, JSC may be the only place anymore that can do it. But anyway, we volunteered to do that as part of our test program as a programmatic requirement, not as testing or watching or confirming anything, but as a prime part of the test program was the man rating of the airlock, and that was done in Houston.
more.
That's an interesting thought. Walt, if my memory serves me correctly, one of the problems we had in the early part of the manned space program was doing some chamber runs with McDonnell Douglas with a two-gas system where we actually lost either the oxygen regulator or the nitrogen regulator in the chamber and almost lost a test subject. And that's when on Apollo we decided to go to 100% oxygen, and that's what led up to the fire on the pad. We went to 100% oxygen at 16 pounds per square inch with an inward opening hatch for another reason. And that's really, if you can realize that 100% oxygen at 16 psi, everything burns. Stainless steel is not self-extinguishing at 16 psi. And of course, that's what we were at the 204, when we had the 204 fire, or Apollo 1 fire on the pad. And it was a function of doing some test work with the confined atmosphere. So you got to be careful. Sometimes you don't overreact to things. And then we went back to a different type of atmosphere.
Liang, did you have a question?
The systems you've been describing today seem to take up a lot of space in the orbiter, like other systems. How did you negotiate with managers and other subsystems, for the space and the volume and the weight that you wanted?
That's a good question, but it's you're asking the wrong person. We're the government. We hired a contractor to design the vehicle. Now, the design aspects of it, the philosophy of it, the functionality of it, we were very, very integral with. But we really didn't, we watched, we audited, we said that looks smart, but we didn't go and say put that cold plate here and put that heat exchanger there. The vehicle integrated design was a Rockwell.
Let me tell you how it was done. Actually, in those years, we didn't have CAD/CAM systems. And what we did is used everything on mock-ups. We did mock-ups. So the system was laid out of what to do and the functions of what they had to do and the plumbing, and this was all laid out in a mock-up. And basically that's how it was negotiated in terms of what you need. In today's environment, you wouldn't do that. You would use electronic capability. You use your CAD/CAM systems. You would actually draw it up on your computer. In fact, the 777 was built that way. The 777 at Boeing was built. They didn't use hard mock-ups. They used electronic mock-ups. And that's what we would do today, and it would be much easier. You would probably call all the engineers together. You would sit down and show how the equipment was laid out, get a satisfactory buy-off on it, and do it much more rapidly, much more quickly. So in the future, what you'll be doing is be actually using a CAD/CAM system or a CAD system to actually negotiate the space you need for it. So that's a good question, and it was based on purely you would get drawings, mock-ups, go out and lay it out in a soft mock-up or a hard mock-up. You'd get the engineers to come out, the manufacturing people to come out. You say, this is how it's going to look, and get a buy-off on it. Today, you wouldn't do it that way. You would do it all electronically. So it would change. Well, let me ask you a question. Of all the work you've done in the shuttle, what was your biggest concern in getting ready to fly or during the flight? What did you have the biggest concern about?
I was young and confident. I don't know that I had a specific area that I was really concerned about.
People right here, right? You're young and confident.
I did recognize, though, but it did result in the integrated test that I showed. I did recognize that we had the most highly integrated thermal control system ever conceived. And it had, as I said, modes within modes. It changed modes with respect to the vehicle phases. It changes mode with respect to operation. We had 9 psi that went to 10.2 psi. We had 8 psi. We had thermal control loops, ammonia boilers, flash evaporators. So I did recognize the sophistication. In fact, we proposed early on to use that large chamber in an integrated vehicle test. Not we, me, but the big we looked at an integrated test like the command service module was tested. And that was viewed to be impractical. There was a cut it off at the bulkhead. You could do the forward cabin part and then do the aft section. But that was viewed to be impractical. But it still was a very integrated design. All the systems engineering that was there created that interdependency. And I think I was smart enough to know that there was certainly some potential risks there. But we did, remember in the very beginning of this, I talked about ownership of all the technical aspects. We had ownership. We believed that what we had done was prudent, appropriate, and we believed it would work. So it wasn't like you bought something and you hope it works.
Can you say a word of what you think? This is looking in your crystal ball about the CEV. Do you think it's going to have a very similar type system, or what, have you thought about that?
Well, we hope so. Our new administrator has sort of a back to the grassroots philosophy, or at least right now. And so we hope that the CEV will be developed with a lot of government involvement, that the government will have ownership, again, of the technical aspects of the design. If that happens, then I think a lot of the experience that's around and a lot of the free thinking and the independence that the government can bring to that. There's another school of thought that says keep the government out of the way and let the contractor go do their thing. And obviously you wouldn't get that position from me, but there are people that believe that's the right way to do it. So
do you think the system will look pretty much like this, or similar to it? Or?
Well, similar, yes, I do think so. I believe that the very tight schedule for the CEV is going to put a lot of pressure on the program manager to go with the tried and true. So I don't think there's going to be innovation that has risk with it. Maybe there'll be innovation that's good engineering, but I think the innovation with risk will be very much minimized because taking shuttle offline in 2010, it's going to be a lot of pressure to get this vehicle finished. So I think that's going to breed some conservatism on the design side.
We talk about considering operation while you're doing the design, but there were always things once the design was made. Well, like you mentioned, once we came up with a requirement for a 10.2 cabin, we had to develop workarounds. And one of the other things that after the system is designed, we then start to figure out how can it fail and work on malfunction procedures. And I know that the malfunction procedure for loss of 2 coolant loops, that was probably the worst simulation case that we ever had to deal with. I'm curious to get your opinion because just, Walt described how we have 2 independent cooling loops so that in principle one failure won't take them both out. Now I don't remember what it was, but they did discover a single point failure somewhere in there, which I think was corrected, but where you could have lost both of the cooling loops with a single failure. I don't know if you...
The only failure I remember is one that John Young used to worry about. It had to do with if you did lose a radiator, that could bleed your accumulator down, and so they did add an isolation valve so they can isolate the radiator side. But the idea was to obviously not lose your fluid with a single hit, that even though you have a nice completely functional thermal control system, it's useless because it has no fluid.
We did have an emergency deorbit procedure for loss of 2 Freon cooling loops, and it was, of all the things that we practiced, that was the hairiest, because it was absolutely time critical. You know, at this point you have no way of getting heat out of the cabin, so you can't ultimately cool your electronics. The cabin gets hot, your electronics get hot, so you have to do an immediate deorbit. Hopefully you're within range of a landing site, and then you turn off all the equipment that you can possibly turn off, including most of your computers. And when you're riding down through entry, you basically watch the temperature of the computer, and as each computer would get up to its failure temperature, you would then switch on the next computer, transfer the data, you know, turn off the computer which is just about failed, and hopefully you could make it to the ground. And I know the instructors who would you know, lead us through this exercise said that the information they had gotten from the thermal analysts was that nobody was really sure whether we could make it. I don't know what your opinion was on that. We practiced it, but you know, obviously, as I think I've told you, nobody's ever died in a simulator, but you never know whether the thermal model that they use in the simulator is really going to duplicate the way the shuttle is going to behave in an absolute emergency situation like that. So we survived in the simulator, but I don't know what you're feeling.
Well, we do address the thermal model accuracy. We do specific testing to validate the thermal model, so we do have pretty good confidence in those. But the real issue in overheat is that when does a piece of equipment stop working in an overheat situation? I mean, there's no magic number. It's not like 143 degrees it's okay and 144 it's not okay. So, and it varies. It varies with age, it varies with equipment, it varies with a lot of things. So there wasn't really a precise answer as to how long you could keep everything functional and come home. Yes?
You talked earlier a little bit about oxygen-nitrogen mixing in the cabin. I was wondering if there's a way to really study that on the ground, since you're not in a a zero-G environment. You know, how there are not pockets of nitrogen sitting around that the astronaut can stick his head into.
Very good. I just forgot to mention that earlier. The testing that we ran, we had to set it up very carefully. So, let's see, maybe I can, probably won't work. But, oh yes it will. Yeah, well, it's all right. It didn't really, if we could get, yeah, I was looking at the ETA slide. The 2 decks, go down a little further. This one. That's the outside, the next slide. Right. If you notice, there's a flight deck and a mid deck, so obviously buoyancy is going to mix that stuff for you. So what we did is we set up a thermal condition where less than 1 degree thermal gradient everywhere in there had to exist before we ran the test. And that was to guarantee that we had no help from circulation, naturally induced circulation. But you're absolutely right. That test would have been a useless test without neutralizing the gravity effects.
And we actually, the first time that I did the spacesuit test in there, we actually used the 10.2 protocol. So I actually had to go in the day before, take the cabin, take that to 10.2, spend the night, and then we could do just a 40-minute pre-breathe. For most of the other tests, when you go in, in order to avoid the inconvenience and expense of staying through the night, you go in early in the morning, and then you're coming right from a sea level environment. So before you go down to 4 psi in the suit, you actually have to pre-breathe pure oxygen for 4 hours. As Walt said, that was the alternative. So you basically just get in your suit, and you can either bring a book and read your book, or they'll pipe music into you if you want to give them a CD, or I guess it was a audio cassette in those days, or they have a little black and white TV monitor that they can share. So, and you just sort of sit there for 4 hours, and then once you've finish the and the problem is you're not allowed to go to sleep. That would be the easiest thing, but they want you actually to move around, because when you're moving your muscles, you're actually then doing a better job of denitrogenating. So you have to stay awake, and if you don't say anything for more than about 10 minutes, they'll pipe something in and say, "Jeff, are you awake?" So. But this was a very, very useful facility. I mean, they used it for all different sorts of things, and it's I guess that was the one new facility which was built for the shuttle.
Yes.
Specifically.
Jeff mentioned several times the 10.2, and I talked about the 9. The 9 was the original design, but the issues with the 9 psi had to do with
you had to take the oxygen percentage got too high, right?
Right, and so there was much concern about flammability. So the idea was if you could raise the pressure up some to 10.2, then that would be less flammability issue. But then the problem became at 10.2 that the suit at 4 psi was too much of a drop. If you're in the bins world diving, somebody mentioned diving earlier, scuba, you can usually use a 2-to-1. So if you don't reduce pressure more than half, you're probably okay. You're probably not going to get the bends. But half of 10.2 is not 4, and the suit's at 4. So there was that issue again. So they bumped the suit up a little bit, and they got it up to 4.3, and went to 10.2 and developed the pre-breathe protocols that made that acceptable. So that's sort of how it balanced out. But that was another operational move later.
Yeah, and as Walt said, you're spending enough time once you get in the suit and you purge all the nitrogen out, and so you're sitting in a pure oxygen environment. You've got to do a bunch of tests and check out, communication tests and cooling tests, so that you basically, you're not losing much time by having to spend 40 minutes pre-breathing. So the whole thing worked out pretty well. Yeah. And it'll be an interesting question how they design the CEV, because the CEV has to be compatible with docking to the space station, which works at a sea level environment. But on the other hand, if you're going to take the CEV into a situation where you want to do a lot of spacewalks, you probably want to be able to operate it at probably more like 8.5 or 9 psi, so that you can go right into a spacesuit without an extensive pre-breathe. And of course, people are always trying to figure out, could we design the spacesuit to work at a higher pressure, but then you give up maneuverability. We'll talk about that in another lecture that I'll be giving on EVA systems. So, Walt, thank you very much.
Oh, enjoyed it.